afternoon to the participants who are watching this live session. So, welcome to everyone today's insightful session titled Beyond Redundancy Exploring the Fail Safe Concept in Aircraft Design. This session is designed to delve deep into the advanced engineering principles that ensure aircraft safety beyond the traditional methods of redundancy. And redundancy is a while crucial and involves the duplicating critical components or functions of a system so that in the event of a malfunction, the backup system takes over. However, in today's session, shift focus towards the concept of fail-safe design, an approach that enables a system to default to a safe mode in case of a failure, minimizing the impact on overall system functionality and ensuring the passenger safety. And fail-safe design in aircraft engineering is a critical consideration that goes beyond simply having the backups. It involves creating a system that, even when parts fail, will inherently minimize the risk and prevent the catastrophic failures. This can include designing parts that degrade gracefully, allowing the aircraft to continue operating safely until the maintenance can be performed. And examples of fail-safe design include the use of materials that show obvious signs of wear before breaking, systems that revert to a neutral state when malfunctioning, and controls that maintain minimal operability under the failure conditions. This approach requires a deep understanding of the behavior of each component under various stress conditions and the interactions between the different parts of the aircraft design systems. In today's session, we will explore the various aspects of fail-safe design strategies from theoretical frameworks to practical applications within the aerospace industry. And experts in the field will discuss the latest innovations in material science and structural engineering and system integration that contribute to safer aircraft designs. By examining the case studies and current research, the participants will gain a comprehensive understanding of how fail-safe mechanisms are integrated into the design process and ensuring that even when individual components fail, the overall system remains operational and safe. This is not only enhance the safety of air travel but also pushes the boundaries of aircraft design and allowing for more resilient and reliable aerospace technologies. And before we start Mr. Suprith's session, I would like to give some sort of introduction about him. So we are pleased to welcome Mr. Suprith as our guest speaker today and currently serving as an assistant professor in the Department of Aeronautical Engineering at Gopalan College of Engineering and Management. Mr. Suprith brings a rich blend of academic and practical experience to the table. His career path showcases a strong commitment to the fields of dynamic, mechanical design, and aerospace structures, where he has significantly contributed through the various roles ranging from engineering to education and mentorship. Mr. Chuprith's professional journey is marked by his proven expertise and in the design and development of mechanical devices and specifically focusing on plastic injection molds and jigs and fixture fabrication. His engineering prose is complemented by his proficiency in using the advanced tools such as MATLAB, CATIA, SolidWorks, and ANSYS, which have been pivotal in solving complex engineering challenges throughout his career. His role at Innovations as a mechanical design engineer underscores his ability to lead the projects from concept through the completion, optimizing designs for manufacturability and enhancing the product development processes. Beyond his technical and engineering capabilities, Mr. Suprith is deeply involved in educational initiatives and demonstrating a passion for enhancing the STEM education through his previous role as a team leader and founder at Technophites. His efforts in organizing the workshops and seminars have impacted many and aiming to kindle a deeper interest in aerospace engineering among the students. And additionally, his involvement with the Vidyanjali Higher Education Volunteer Program and reflects his dedication to contributing to the community and fostering educational growth. His academic background with an MTech in aerospace structures and design engineering from IAAEM and Jain University and a BTech in Aeronautical Engineering from Singania University provides him with a solid foundation to inspire and educate the future engineers. And today, Mr. Suprith will share the valuable insights into the latest advancements and methodologies in aerospace structures and dynamic mechanical design. At the end, I would like to introduce the motto of Mr. Suprith: engineering innovation, educating for impact. So, I would like to hand over the session to Mr. Supreet, and also thanks a lot for joining us today. And over to you, sir.
Thank you. Thank you so much for your warm welcome. So, can I start the session now?
Yeah, sure, sir.
Yeah. Is my screen visible now?
Yeah, yes, sir.
Well, good afternoon, everyone who are present in the meeting. So, you might be wondering, beyond redundancy, like what exactly it sounds like exploring the fail-safe concept. Like you have both in the name, fail as well as safe. So, student might be wondering, like, how exactly it sounds like fail-safe. If it fails, how it can be a safe? These questions everyone might be having. Before getting into an aerospace, generally let's talk about like how many accidents happens in a road in India for every year. Suppose if you take a survey of 2022, a road accident number was somewhere around 4,60,000 per year. 4,60,000. Out of that, 1,68,000 fatalities were happened. That means like every year so many accidents are happening, so many people are dying. But if you take the same thing in the aerospace, suppose if you take an aircraft in an aviation, how many accidents you will report every year? It's not like a 4 lakh 60 whatever you see in the roads. But thing is, what we need to understand is why that thing is happening in the road, why not in the aircrafts? Why we don't see accidents or fatalities in the aircraft often? It happens. It's not like it won't happen, but it happens, but not as often as the roads. So, getting into this, we will try to understand what is fail safe. So, you might be wondering, as I told you, something has failed, but still, how can it be safe? So, let me give you a small example of everyday's activity, whatever we do. You might be taking a lunch box with you every day. So, you might be packing the sambar in a Tupperware or any other container, but still, after even having an Tupperware boxes, you still wrap it with an covers. So why do we do that generally? Suppose if the this thing Tupperware cap opens, it's just a backup that we are having another cover so that it won't spill into the bag that we are carrying. So this is what the backup means. So everywhere in your houses also you might be having a UPS. Why do we have an UPS? Whenever there's a power cut, we need a backup. So this is what the system is fail safe. We can general example what I can give is this is what. See, suppose you might be having a car. So every car will come with a stepney. Why do we have a stepney? Of course, whenever there is a puncture, so you will have a backup. So this is how things works. Like fail safe is this is how it works. So something has failed, but still you are safe enough to move forward. Suppose if it is a car, you are safe enough to move further. In case of your tiffin box, of course, even if the cap opens, of course you are safe from spilling it. So in general, like if you go for an aerospace, this matters a lot because we have design philosophy. In design philosophy, generally we go with safe life and fail safe. So safe life is like you might be having a two-wheeler. So what happens in a two-wheeler, for every general service you might be leaving general service for every 3,000 kilometers or so. So like after a series of services, there will be a change in engine oil, and there are change in air filters, there are change in oil filters, there are predetermined lifespan of an components of an each and every parts whatever we have it. In aerospace also we have that. We have a maintenance log where we will be mentioned after series of hours of flying we need to change that parts. So during this changing, whatever, see, with what we do, how we know that this part will work only till, let's say, suppose if a oil filter, let's say, oil filter will work only for 5,000 kilometers. After 5,000 kilometers, I want to change. But how will we know that we have to change? We will do the reliability testing of the product. Before manufacturing, we will do the analysis of the product, and after manufacturing, we will do the reliability testing of the product. By doing this testing, what we will understand, like after certain time when it fails, we think that is the failure life of that component. So what we do, we fix the safe life for that. That safe life will be generally just less than 50% of whatever we have achieved in the reliability testing. So you can imagine, suppose if the oil filter is capable of running up to 10k kilometers, but we are restricting it to a 5k, that means we are making it more safe. So aircraft engine, whatever we have manufactured, I say it can run up to uh, 15 to 25 years, 15 to 20 years, let's take 15 to 20 years, it can run safely with the proper maintenance. But still, when we test it in a reliability testing, it can go up to 50 years. So what we are doing, we are restricting that so that we won't use it after, because we cannot get the exact moments reaction on those engines. So what happens, it will become safe life. So after that we'll retire it, we won't continue, because it's just like our human bodies. See, after we cross 65, we don't know, like even a small things might have hurt us bad, or we may fell and we may die. So all these things happen. So what happens, after certain ages we prefer to be safe. So that is safe life. So that generally, that's what 65, it's like a retirement age. Why have we restricted that as a retirement age? It is a safe life. We have a predetermined lifespan. So after that, we know it may work or it may not work. So that is why we have done the schedule, the safe life in most of the components, like in cars or in aerospace. We have the safe life as well as fail safe. Some components work on safe life, the general maintenance, whatever the parts we are doing, those under all those things comes under safe life. Now coming to fail safe, see, safe life is again the component. Suppose if you take a fail safe, this is like an backup, very automatic safety that we have in an aerospace. It's not just only in aerospace, even in automobiles nowadays they are including all the safety features. But let's say it started with the aerospace, because we have taken the lot of case studies where we have seen the fatalities, and we came up with those ideas, the engineers came up with those ideas, so that if you include this fail safe, even some components fails on board, so it is still safe to fly and come back to the ground. So coming to the redundancy is like extra component. You can say a redundancy is like something extra that we have, even though our team is full. We always have a backup person in our team, so that if some workload is heavy, so that he can come and play his role. And of course, fail safe, it is most of the time we design it only for the emergency procedures. Like whenever there is an emergency, this fail safe will activate and it will keep us safe from it. But in this design philosophy, we will keep it as our objectives. These are the three objectives that we keep it. But how are we going to implement this in the aircraft design? Because whenever the aircraft has been manufacturing, before manufacturing, there are lot of procedure that you have to go. You have to design an aircraft, you have to make a sizing of each and every components, from right from your fuselage to engines to every control surfaces, whatever the electronics that you are using, all those things have to play an important role in that. So this design itself, we have to follow this objective. So going to the structure, the primary thing of any component or any automobiles or any aircraft, whatever, we want a structural components. So coming to the structural components, you have to have a chassis. If you see a car, you will have a chassis. On chassis, we are going to bond everything, like a engine, seats, all those things. Everything comes on the chassis. So you have to have a redundant chassis first of all. So in the chassis, if you take a structures, you know, most of the structure students who are attending this sessions, they might be knowing this determinant structure and indeterminate structures. Preliminary, what we can say is determinant is something which is stable. Whatever the automobiles that we are using, and whatever the bridges you are seeing, and whatever the other structural components, buildings you are seeing, those are all stable structures, which means it will be just stable, even though you don't need to have any other equations to solve this. It's just a normally a continued equation is enough to derive all the equations on the structure. Whereas this indeterminate structure, whatever we have, those things is the thing we use in the aircraft structural components, where here we have a redundancy in the structures. Why are we keeping that redundancy is, see, redundancy, as I told you earlier, thing is, suppose if you have a, you can imagine the trusses, we have an indeterminate truss and truss, determinate truss, where the extra member will be there. As I told you, as a backup, extra member will be. Those structure, indeterminate structures, they are not stable. Generally, it is not stable. What happens, suppose if one member fails, then that structure, whatever indeterminate structure we have, that will become stable by becoming a determinate structure. That is how it's going to play vital role in a. Suppose if I say, you can see so many longer ends are running here, and so many strings are running over here, and so if one component fails, it won't let the next component to fail. That is what the fail safe actually working in the structures. So structurally, the aircraft wing you can take, or aircraft fuselage, or even a landing gear mounting, all those things, they are designed such a way that even if something fails, it won't let the other neighboral parts to fail. So coming to the redundancy, as I told you, redundancy is like extra power that we keep, extra backup we are keeping in the aircraft. In an aircraft design, generally you might have seen in commercial airlines, it will be having multiple engines. If you take a private, again, private will also have a multiple engines. In some cases, they will be having a single engines and dual hydraulic systems. We will see those are the just redundancy parts. These are the general parts. Apart from that, again, subdivisions. You can go n number of parts where it is acting as a backup. We can list it out in the aerospace, because most of the things are in the backup in aerospace. And coming to electrical systems, again, we have so many backup things. Suppose if one thing fails, the another things will start working there. So that is what the general redundancy is. So coming to the aircraft system redundancy to rescue, suppose I won't go much deeper into the concept. I will just try to brief up in the general aircraft design. So here you can see this is the maintenance manual of Boeing 777. Here you can see there are three actuators actually. Generally, we need only one actuator to move the rudder. But in this case, you can see the rudder over here, this rudder, and we need to move that rudder. And I guess most of you are aware of why are we using the rudder to move the aircraft in a yawing position. So you can see here, this is the rudder part. So this is a control surface, so that if you move this rudder, the aircraft will have a movement, yawing movement. So for that, we have three actuators there. So generally, if one fails, the second one will come into activate. Suppose the second one fails and third one, which is very rare case, the third one. Suppose, let's say, in some cases where the first one failed and still second one came into an exist and it's still maintaining it the position like this, and suddenly the second one fails and still it's okay, it's working, and with some other problems, maybe the third one also failed. So all of them failed, and the rudder has tilted in another let's say it has tilted in the left. So what happens if the rudder is tilted in the left? Your aircraft will be yawing towards the right. So now what can we do? Suppose if this is the condition and all three actuators has failed, but do you think the aircraft will yaw only towards the right and we don't have any control on the aircraft and it will fail? Definitely no, it won't fail. Even in this condition, when all these three things fails, there are chances of still coming to the ground safely. And I will explain you how that things is going to happen. The same situation might happen with your elevators. You can see over here, these are the elevators. This will help us in the lifting of an aircraft. And again, suppose if this tilts down the elevator, whatever you are seeing, and you will have a sufficient lift, but if that keeps in the position, it won't come back. Suppose actuators fails, so what happens? The time the aircraft keeps on lifting, but how will you get it down? So again, there are chances. That's what that we will see. How are we going that in deep? How are we going to get the plane on the ground safely even after failure of these three actuators? These are already on a backup, but still those things failed, and how are we going to come back? So generally, as I told you, most of you are not aware of how the things works on the control surfaces. These are the control surfaces I can see. These are the ailerons, which will help us in a roll, and elevator, as I told you, help us in the pitching moment, and rudder, it is helping in the yawing moment. So these are the primary aircraft structures where we will give more and more importance, because something which will have a mechanical movement usually fails. That is what happened if you see an mobile eras recently, like 1 year 2 years back, we got an pop-up camera cell phones, but it did not go well in the market for a few days, because what happens whenever there is a mechanical system, there will be a failure. So whenever there is a failure, you should always have a backup. Whenever something is moving, obviously, so many stuffs will be included in integrated in that, so there are chances of failure. So how to come up with a new idea? Whenever something fails, you have to have a backup. So that backups, we have it in the aircraft design. Before manufacturing only, we have pre-designed it such a way that there are so many conditions, we don't know what exactly will happen when you are in the air. So we have to keep things back up before we send the airborne the flights. So coming to the generator, aircraft generally have an four generators mainly. That is main generator. Main generator, it's like an whatever the engines that we are using here. These are the main generator. But this main generator needs to be powered on using the auxiliary power unit. That we will see in the tail portion of an any aircraft. You might have seen some exhaust going out of an aircraft structure. So that is our APU, where APU is just like your normal jet engine, where it will power on first and it will start running as an engine, and then it will generate the power, and it will help in the cabin air, AC, air conditioning, all those things, and it will power up the engines that we have. Once the engines are on, this engines whatever we have on the wings, that will be a main generator for an entire aircraft, that will give the generation for power that is required for an entire aircraft. Electrical power, all those things is taken away from this wing engines, whatever it is mounted. So APU, it will take care of a backup. It is again a backup. Yeah, APU will be in a backup. Once the aircraft is airborne, that will be as a backup. It will always be running. So whenever the loss of engine is there, APU will take care of it. So, and apart from that, we have one small rat, you can see ram air turbine, which is here. This is the small one, but it is a very crucial one. I will say why it is a crucial one. This may look small, but it has saved more than 40,000 of lives in a year. Like, it will save because it has such an impact on an aircraft design. And we have a ground power unit. Whenever you go to an airport, you might be seeing a vehicle standing nearby and connected to an aircraft. Generally, those are the ground power unit, where the power will be transmitted from the ground vehicle to turn on the engines. So coming to, as I told you, this ram air turbine, it will play an important role in an aircraft. Thing is, as I earlier told, let's say there is a situation where one engine failed, and my aircraft is still stable. Suppose if you take a Boeing 747, generally it will have four engines. Out of four engines, suppose let's say one right engine has failed, right outermost engine has failed. I have still one more engine in the right and two more engines in the left. So what happens? The thrust produced in the right will become less. So if it become less, what happens? The aircraft will start yawing towards the right, because left thrust is more. So what can we do that time? I can reduce the thrust from the left so that it will be still stable and it can fly safely. So this is how the things work. But who is going to do all these things is, it's a pilot's job. The pilot will be trained such a way that if something happened catastrophic like this on air, so he will have to monitor the engine thrust so that it will still be stable. Suppose let's say there are some situations where, let's say, see, like thousands of birds are flying in the air. All of a sudden the flight will pass through that birds, and all the engines will be hit by the birds, and engine fails, all four engine fail. So in such cases, what happens? So right now I don't have any thrust in all the engines. So aircraft is airborne. Let's say it is on almost on 12,000 feet or something. So is it possible to land it back when all engines are failed? You can imagine, it's like, just imagine your car with engine failure. Can you get that car to the next garage or something like that without help of a towing vehicle? Obviously no, because it will be either seized, means obviously you cannot even move. You have to get a tow and you have to tow your vehicle for the garage. Whereas in this case, it's not the stuff. Suppose if all my engines fails, you can see this rat, for this entire big aircraft, this is the small rat that you can see. It is a power generator unit. So the main function of this rat is to power the aircraft primary electrical, just like your joystick to control the control surface and instruments that you want to monitor the aircraft. Only primary sources you will get, not the entire aircraft. So that primary sources, whatever the electric that is required, that is more than enough for a pilot to land the airplane safely to the nearest airport. It's not like he can go to the destination, but he can land the aircraft with the nearest airport safely. So so this is about when the engine fails. So now coming into when an aircraft is airborne and it is flying at certain altitude, at certain speed, so it will it will have a radar that will be monitoring the entire air nearby. Any aircrafts are coming or like that, it will be monitoring that. So we have a system called TCAS in an aircraft, that is traffic collision avoidance system, that is inbuilt in the system, where that keeps on monitoring the air around it, so that if there are any other aircrafts or any other bigger bodies are nearby to it, it will immediately tell the autopilot. There will be an autopilot in an aircraft, or it can be monitored by the pilots. So it will pass an information that there are nearby aircraft. So what does that that TCAS do is generally it will communicate between two aircraft. This is an automated system. TCAS will be in both the aircraft. All the commercial airlines will be having TCAS. So what happens? This will pass an information for both the aircraft. For one aircraft, it will ask to climb, and another aircraft it will be asked to descend. So this thing, either suppose if it is in a TA region, generally it will take its own decision. If it's an autopilot, the autopilot will take care of it. One aircraft will climb and aircraft will descend, and it will pass without any collision. But there are, when it reaches the RA regions, there are certain regions where they have to coordinate with the air traffic control and ask whether the TCAS is true. If the TCAS is true, then they have to ask for the air traffic control what to the procedure for that. The air traffic controller, he might also say that to climb or change the position. So these things can be avoided, the collision. This is what the fail-safe is. Suppose if imagine we have a TCAS and there are aircraft which will be on the same position flying head to head. So if this is not there, the collision will happen, and we can imagine what are the fatalities it can happen. Like 200 plus passengers will be there. So it will be a catastrophic, and of course it will be flying over the cities sometimes. So if it falls, there will be a lot more fatalities in the ground. So this is one of the fail-safe design that aircraft has in an instrumentations. And you can just see, I have three case studies here, like which is a miracle in an aircraft design. One is Boeing 737-200, like carrying 89 passengers. You can see how exactly the structure has failed on air. This is what happened when aircraft was on air. So the almost fuselage structure only flew off, but still the pilot managed to land this safely. So you can imagine, say, suppose something failed like this, and but still the pilot could land it safely, means the redundancy in aircraft is truly amazing. Like it is so safe. It's like if the pilot is skillful enough to work on this, like aircraft will cooperate with them. And you can see where elevator has been broken, but still, as I told you, when the elevator is become, I told you like how exactly we are going to do. I will explain in the next slide. Like even after all this fail safe design, if something fails, there are chances of still having a safe flight. That we will see how we are going to do. That is thing is, what are the next step that fail safe design we are going to take. So you can see the fighter jet with only half wing, the other half is on. Generally wingspan of an fighter jets will be very low, and you can imagine, even if the half is done, but still pilot is managed to bring it back to the ground. So if you take a fighter aircraft, there also we have an fail safe, where, see, thing is, in a commercial airlines, what happens, there are 200 plus people they will be carrying. So obviously the safety is the most priority in an commercial airlines. Whereas in a fighter aircraft, we have to compromise in certain stages, where we have to compromise on the aircraft structure stability or redundancy due to the structural load, weight, all those things. But we have other features where it is safer for the pilots to eject and save their lives, because here the cost of the aircraft will be, of course, more, just like our commercial airlines. But thing is, the pilot life is what matters. But this ejection seat, you can imagine, why can't we have this in a commercial aircraft? But this ejection seat, this procedure of ejection is not simple. You can, I have mentioned here, you can see the ejection of seat, it will take up to 20 Gs in certain condition if it is flying in an Mach number 1. So you can imagine putting so much pressure on you, almost 20 Gs. Right now we are in a 1 G. So you can imagine 20 Gs of pressure on you at a time. You cannot withstand that pressure. There are sometimes you may die also. So this condition and these features we cannot include in a commercial aircraft. This can be only included and trained for an fighter pilots only. And we have an emergency procedure where certain aircraft, recently even India has landed their fighter aircraft in the highways, where the runway is shorter and the aircraft has to be stopped in the certain meters itself. So these things are safety features that we have included in the fighter aircraft, where even if something happens suddenly, let's say some malfunction is happening in the fighter aircraft and it doesn't have any airport nearby, or even if the airports are nearby, the runway is not long enough to land the aircraft that is according to its capacity. So in such cases, we have a backup parachutes or other braking system where it can brake and get the aircraft within certain distance. And if you see a navy aircraft, we will have a tail hook and snag arresting wires on the flight decks. This is again very tough procedure for any aircraft. This includes all the structural analysis of an aircraft, because the aircraft will be flying around when it is approaching, it will be coming around 500 kilometers per hour to 600 kilometers per hour, and it will just snatch into that wire and it has to stop immediately, because pilot cannot slow down the aircraft when it is arriving to the deck. Because what happens, suppose let's say there will be a series of snacks. You can see here there are so many wires here. Either one of it has to catch and stop the aircraft. Suppose if none catches, what happens, the if the flight is at very slow speed, it will go and dive into an ocean. So if that things should not happen, he has to keep his thrust at the maximum, so that even if these three things did not catch, he has to again fly back and he has to come back and re-land it. So these things and all is like, it's all combination of pilot skill and the pure engineering behind the all the component that is used in this. So as I told you, I was telling about how still the things are can be saved even after catastrophic failures in an aircraft, even after having series of failures of all the backup system, but still a pilot can land the flight safely. That is through our flight simulators. This is a wonder of any engineering piece. So the pilots will be trained in the similar simulators for n number of situations. Like they will take in various conditions, like various scenarios, and they will be trained and they will be certified. Of course, it is mandatory to get the certification of an simulator every now and then for an pilots to make them much more active. Because in a commercial airlines, the pilots generally what they do, generally if you fly, generally they'll take off and they put everything in an stable manner and they put the entire aircraft in autopilot. Then autopilot will take care of the entire flight journey for another 1 hour or 2 hour depending upon the flight hours. And again, whenever he is approaching for a landing, then he switch off the autopilot, then he gain all the power control on the aircraft and he will land. This is, and we have ILS also, intelligent landing system, where even the landing and takeoff will be taken care by the autopilot. So in some airport we have that. But of course, during the flight, the pilots will be busy in these two tasks, the takeoff and landing. So suppose in between this autopilot, when it is working, if some situations happens, like as I told you, if the rudder broke or even if the elevator broke, how the pilots gonna react for it and how they are going to land it, those things can be achieved with this flight simulator. One advantage of this is we can do unlimited testing on this flight simulators. We can have a different kind of situation where we cannot do that in a real life. Of course, we cannot try turning off all the engines in the airborne and check how to land it, of course. So we have to do those things in a simulator so that you will get an idea what you have to do when there is chances of like this, like when four engines fail. As I told you, when four engines fail, there will be a rat, and utilizing that rat, the pilots will be having a very good knowledge of how much distance they can travel, so that if the nearest airport is so and so, they will know, they can descend the aircraft in a slow manner so that they will land at a nearest airport. So that's what they do. Suppose let's say if there is no airport near at all, if there is any highways or plain surfaces, or even if a river or a lake, the pilots will be trained enough to land it on the rivers or even the oceans. In some cases, even the pilots has landed their flights in the oceans. See, that's what the fail safe doesn't only include the structures or the engines or the components. It's fail safe by design. It is for even for pilots. The pilots will be trained enough to say even after failure they are safe and in a safe hands. That's what the entire fail safe components is. So, as I earlier told you, like if the elevator has been struck in a right position and the aircraft is pulling, yawing at left, how will the pilot will still manage to bring it to a stable position? So, it's a general physics you can see. See, suppose if I something is pulling like this, how to work on this? I have to apply something in this part so that it will come back to the position. So, what can I do? I can reduce the thrust in the other two engines on the right, and I can increase the thrust in the left. So what happens if the thrust is increasing? Obviously, it will start pulling the aircraft in a stable manner. So this way, the pilot can achieve the stability there. So this is how the stability can achieved in an aircraft. If one component failed even after three backups, so have another backups. So this backups is like a physics procedure. So he has to know that physics. So if he gives some force on this, it will come back to a stable position. Same thing happens with your elevators. When the elevator is down and your aircraft is pitching up. So in this cases, what can we do? We have a flaps, and we can reduce the thrust, and you can get back the aircraft to the ground. So these are the pilot training session that will be done in a flight simulator, and even in a real life, they have done all this in an emergency procedure. So whenever there is an emergency, so aircraft design as an fail-safe components. So this fail-safe components will help the entire aviation management for the pilots to land the aircraft safely. When it comes to an fighter aircraft, we might have seen most of the fighter aircraft, it will crash. So those cannot be avoided. So what the pilots do, they will take the aircraft to the nearest where there will be no persons. So they will try to crash the aircraft there and eject themselves for a safer life. Even after ejecting, they will undergo certain medical procedures, because there will be excess of force on them, so it may cause them to have some medical emergencies. So apart from that, wow, what are the flight simulator advantages? They can get the latest emergencies, like what are the situations they can face, due to the based on the case studies, like what are they can evaluate themselves, how exactly their reactions time will be, how exactly if something fails, how exactly they have to work on the aircraft. All those things they can learn in this simulator. And even procedure of evaluation, they will know like what exactly the aircraft is working. Suppose if something fails, here you can see Boeing 787 simulator, so you will know exactly it's just a replica of a 787. Whatever 787 is in working condition in a real life, the same thing is in a simulator. So you will know, you will give a different scenarios, and you will understand how exactly aircraft will behave in that different scenarios, how to get it back. Suppose if something is not able to recover, so in such case, what are the things you have to improvise in an aircraft? All those things can be achieved using this simulator. And regulatory compliance, of course, they can what they can do, they can seriously go for this training process, they can get certifications, so pilots can upgrade themselves with the latest these things. So far I have discussed only in the aircraft. Suppose if an aircraft fails, what are the things? If the engine fails, if the landing gear fails, yeah. Coming to the landing gear, of course, even if the landing gear, both the landing gear, if doesn't uh, retract whenever it is landing. So in such cases, what the pilots has to do, again, they will be trained to belly land. All those things are trained. That's what. Even the flight is still stable to save the lives. So now coming to the fail safe in helicopters. Of course, in helicopters also most of the structural components are designed in a fail safe manner. Even if some structures inside the aircraft chassis fails, it won't let the other structure to fail. So it is still safe. So apart from that, we have a feature in an helicopters. Apart from, like in an aircraft, what happens when the aircraft is in airborne? We will have a lifting, major lifting device is our wing. So we have a wing. So we can slow down due to that descending, we can achieve the lift and we can land it at the nearest airport. But when it comes to an helicopter, it has an VTOL capacity, right? Vertical takeoff and landing capacity. So in such cases, if it is at certain altitude and suddenly the engine fails, but still the helicopter is also again safe enough to land. So that procedure is called auto rotation. What happens in auto rotation is, suppose let's say the helicopter is flying at certain altitude and suddenly engine fails, so the pilot has to adjust the rotor blade in a such an angle such that the rpm of that will be achieved by backwashing whatever the direction of the flight. If you change the rotor, you can see here the airflow around the rotor blade will be changed, so that the rotor will start rotating. You might have played so many like paper helicopters or an plastic helicopters, whatever we get it. If you throw it out on the sky, it will come back in a rotation manner. That's how it works. Just the air passes with the rotor blade and it will start rotating. So this auto rotation is sufficient enough not to fly, but to land the helicopter. So the pilot will adjust this one and he will manage the airspeed around that auto rotation. He will slowly start descending the aircraft, and he will touch down. Sometimes it will be a soft touch down, sometimes it will be dragging up to some extent. So this is what it does. And after that, they will, of course, there will be an post landing procedure where they have to check for the safety features and emergency communication. They have to communicate with the ATC for emergency. And post evaluation, like this is the most important thing for every failures, whatever flight, even it is in a flight or even it is an helicopter that they do. What they do, they just try to see what exactly failed and why exactly it failed. So this is what gives us an idea what improvisations we can do, what are the backups we can improve so that these things won't happen. This is how the engineering has evolved. What we do, we take the problems. There is certain problem where something has failed. So I will take up that problem. I will try to work on it. What are the things we can implement? Suppose if there is any backup, I can improve the backup there so that we can have a safety. Or else what we can do, if I can improve the components itself, I can improve. Just like our yeah, cars right now, most of the cars will be equipped with electronics, most of the electronics. So what does it do? It will give you real-time data for your cars. Now you can see the mileage, whatever the you are getting in your vehicles. Just like that, we have in backups. So many technologies has been coming so that you will know what you have to do in the next. That is what matters. So this is how it works as a fail-safe in an helicopters also, as well as in your aircraft also. Whenever something fails, we have to do the entire post-flight evaluation so that you will know what exactly failed, even after having three actuators. Why the three actuators failed? What are the conditions made it fail? So that we will know for the next design we have to make sure that even in those conditions these three things should not fail. Suppose we cannot achieve something where the components we cannot achieve in that stable manner,
Yeah.
then we have to have another backup so that even after these three things fail there should be another backup. Suppose if it is not there, of course we have a pilot training where they will be acting as our fail safe component here. So I think like this is how the fail-safe entirely in an aircraft design procedure works, and this is how. Suppose if you are after listening to this session, you might be very confident to travel in an aircraft. So many people might have been very scared to travel in an aircraft so far, but after listening to this and after knowing so many backups, you might be getting some confidence enough to travel in an aircraft. See, that's what I'm saying. See, road safety, of course, we don't concentrate much because a car, let's say, it will cost you around 15, maximum up to 45 in a general cars. So, but an aircraft, you can imagine they are investing in the aircraft industries like management, aviation management. They're investing on airlines are investing on crores, thousands of crores, and the people who are traveling, of course, they will be worth so much. The lives are worth so much, so they have to do all this component test and fail safe test, safe life test before taking the passenger in the flight. So, but in the cars, right now we are doing a lot more things in a cars as well. We have NCAP ratings, all those things, safety feature. We have 8 airbags, 12 airbags. But thing is, at the end of the day, it also matters with an pilots as in the aircraft. But in a road accident, it matters with an person who is driving. If the person who is driving is not able to control the vehicle the way we have to, then obviously there will be a road accident. So again, the training of an drivers is very very important. Just like in our airlines, where the pilots will be trained even after getting a 15 year 20 years of experience, they will be training in a simulators because we don't know what exactly will happen in an air. So similarly, in an cars or bikes, you should be aware, you should be following all the traffic violations. In airlines they will follow the strict violations because it's a very mandatory uh, to do those things. But in roads we generally neglect it, but which is very life consuming. As I told you, 168 people are lost their life during 2021 to 22. So it is very important to have this fail safe concepts in our real life as well, not only in aerospace. So, by saying this, I guess you all got a clear, brief view of how exactly the fail-safe of an design philosophy works in helicopter, aircraft, how exactly it is designed, how safer it is, all those things. I guess you got a brief idea of how exactly it works. We can go in depth, but thing is like it will be more and more complicated. Thing is, if it is safe, remember one thing: it's more complicated. The engineering is more complex, so that the things are safe. We have to work so much that even as I told you, if it is a normal truss, if it is a stable truss, the calculation would be very easy and fair enough. But when you are implementing one redundant structure in that, you need to solve so many equations to get the answers on the each individual member. So why are we making it more complex? To make it more safer. So that is how the things work. So I would be open for any question and answers from the audience as well. So it would be great for an interaction.
Yeah, thank you, sir. Thank you for the presentation. Hello, sir.
Hello.
Yeah, okay, sir. I have some questions here.
Yeah, sure, sure.
Yeah, okay. So, how can the fail-safe design principles be applied to the development of unmanned aerial vehicles to ensure the safety and increasingly crowded skies?
Yeah, yeah, that's what. See, even in the unmanned aerial vehicles, again, they are equipped with the TCAS systems. This TCAS system, what they will do, they will be sending the signals for both aircraft as well as this UAVs. So they will be having communications. So whenever the aircraft is flying nearby, it will know this UAV is flying nearby. So it will send the signals to for an UAV so that UAV will descend or climb. Usually it will descend because UAVs generally we don't expect them to climb as much as a commercial airline does, so it will be in a lower ranges. It will
Okay,
generally
thank
fly
you.
in a lower altitudes compared to commercial aircraft. So yeah, they will have a communication generally, and even control system. Whatever the UAV will have a control system which will be controlled in an chamber. So they will have this information and they will control it. They will descend it and they will avoid this collision system. As well as if you say like suppose something catastrophic happened in an UAV, and still nowadays we are working more on UAVs so that even something fails, the engine fails, there will be a parachute which will be evacuating and it will safe landly.
Yeah,
So, any
okay.
other
So, what
questions?
are the challenges? Yeah, what are the challenges and the solutions in designing fail-safe system that can effectively function in both normal and extreme conditions, such as emergencies or combat situations?
Yeah, that's what I told. See, it's a fail safe and safe life. We are doing it together so that, see, the margin value, whatever we are designing is, let's say, 100. It's just in general, like 100 kilometers. Let's say the component is capable of running only 100 kilometers in a general. But when we are testing the reliability text component of that component, it will go up to 200. In my test result, it will fail in 200 kilometers. But in the marking, I'm saying it can run only to 100, so that it won't be used after 100. So this is how in the emergency procedure we are monitoring such a way that instead of carrying that component further, we will change it in the 100 kilometers, so it will become more safer. Even though it is safe enough, even after 100 kilometers, we are better replacing it.
Okay. Then, how can the integration of distributed control system in aircraft enhance the effectiveness of fail-safe designs?
Integration of control system, as I told you, see, that's what the autopilot will have its own control system. So it will be judging the entire aircraft. Once the aircraft is in a stable position, this autopilot will take over it and it will do all the maneuvers that is required. But even after that, sometimes it fails. There are certain, let's take a pitot tube is not working. So the information, the input that the aircraft autopilot is getting is not true. So then obviously it will, because it doesn't know that it is wrong, but pilot will be knowing. So the pilot will be keep on monitoring this instrumentation of the control system, how it is going on. Suppose if he sees something is not working, then obviously he will take over the control. Even if the pitot tube is not working, due to his experience, he is able to control the flight to bring it back to the stable position.
Okay, thank you, sir. So, what are the implications of incorporating the autonomous decision-making processes in fail-safe system for critical aircraft operations?
Yeah, critical aircraft operations where the main decision making will be with the pilots generally, because when such emergencies happens in a critical conditions, the skill of a pilot matters a lot. So they have to undergo series of tests in a simulator, as I told. So then only they will know how to face in situations there. Then only they can bring it back safe. So training is what matters and decision making is how the reaction of an pilot at that time, how the way of thinking of him is dependent. Like most of the pilots, they are very skilled enough, they know what exactly they have to do when something fails. The reaction time will be very quick from them.
Yeah, okay. Okay, so this is my last question. So, can the
Hmm.
concept of fail operational systems, where the system remains operational but in a degraded mode after a failure, be an effective alternative or complement to fail-safe systems in certain aircraft applications?
Yeah, like if you consider like if they are even after failure, yes, it is it can like still it is safer, like that's what it is. Like so far I have discussed, even after failing, the implementation of this fail safe, like how exactly it will be decided, it's not like decided by a single person. there will be a series of tests that will be done after the design itself. This entire design process is like a very long process. This entire after design process will be a series of clarifications will be done, series of tests will be done on the design itself. There will be analysis that will be going on. So they will test each and every aspect of the design before manufacturing or implementing on an aircraft. So yes, it is very necessary, and it will implement. So series of certifications will be done, then only it will be implemented.
Okay, sir. Thank you for the useful answers, sir. The answers are very useful. I hope the access and the participants can understand about that. So finally, so on behalf of everyone here today, I extend a heartfelt vote of thanks to Mr. Subrith for his outstanding contribution to our session on Beyond Redundancy, exploring the fail-safe concept in aircraft design. Mr. Suprith, deep insights and experts' knowledge have significantly enriched our understanding of innovative engineering solutions that go beyond the traditional safety measures in aircraft design. And Mr. Suprith's engaging presentation and detailed analysis of dynamic mechanical design and aerospace structures have provided us with a comprehensive view of how advanced engineering techniques and tools can be leveraged to enhance the aircraft safety and reliability. His practical examples and experiences as both an educator as a design engineer have vividly illustrated the critical role of fail-safe mechanisms in modern aerospace engineering. We are truly grateful for Mr. Supreet's willingness to share his expertise with us, and his passion for advancing aerospace technology and his commitment to educating the future engineers are truly inspiring. So thank you, Mr. Supreet, for your invaluable time and efforts which have contributed immensely to the success of this session. We look forward to future collaborations and learning opportunities with you. So thank you, sir.
Sure,
Thank you so
sure.
much.
Thank you so much.
Yes.
Thank you so much for giving these opportunities. Thank you.
Yeah, sure, sir. Thank you, sir. Yeah.